So next it says that an experiment was performed to determine how the strength of the magnetic field affects the value of the induced current. Readings of the speed of movement of the rod, U, and induced current I were obtained and recorded in Table 1. Table 1 shows the readings below. So we see that, we have a table like this, and it is partially completed. And one of the things that your exam will often facilitate is an incomplete table or a partially completed table, which they expect you to be able to fully complete. So in this case, now it says that given that the rod has a resistance of 25 ohms, we're to use Ohm's law to complete table 1 by calculating the induced EMF V. So from Ohm's law, we know V is equal to I times R. So in this case now, if we are given the induced current and we know that the resistance is 25 ohms, we can calculate the induced EMF for each instance. So let's get out the calculator and do that. And one of the things that's going to become very handy in our exam is the use of our scientific calculator. So we always want to ensure that we are quite comfortable with using the scientific calculator. So whenever you're working practice questions, you always want to make sure that you're using up your scientific calculators so that you are quite comfortable with them. So in this case now we're going to use Ohm's law, where V is equal to I times R. So in this case now we're going to say that I is 0.0045, right, and R is 25 ohms, so we'll multiply by 25, and we're going to get, in this case, that our induced EMF is 0.11. And since we have all these values to 3 decimal place, we're going to also express our answer to 3 decimal place. So that's also something to consider when we are completing the table. We want to keep the number of decimal place consistent. So next one now, we have 0.0215, which is for this one, and we're going to multiply by the resistance, which is 25, and we get 0.538. Next one, we have 0.03, and we multiply that by 25, and this becomes 0.750. Now, one of the things that students oftentimes get worried by is when they see a table and we have these small or these decimal values working with. So oftentimes, students get a little bit flustered when they see values like these. So we're gonna go through and see how exactly we can actually plot our graph and take these values into consideration. So it was 3.8. All right, so here we have our table completed. Now it says that we're to use the results from table 1 to plot a graph of induced EMF V against speed of movement on the grid paper provided on page 2 or page 7, and we're going to draw the line of best fit through the point. So first thing we're going to do is we're going to draw up our axes. Okay, so I've drawn up my axes and I've labeled each axis with the required quantity. So since they say we should plot a graph of induced EMF against speed, then we will have induced EMF on the y-axis and the speed of movement on the x-axis, just as what we have now. Next thing that we need to do now is to determine a suitable scale. So again, we're plotting induced EMF on the y-axis and the speed of movement on the x-axis. Now, as we see, we have some rather small values working with. Now, one of the things that we can do in terms of our analysis right here is we can choose to express these values in standard form. Now we're going to see that if we express each value in standard form, this one will become 1.13 times 10 to the minus 1, right? And this one will become 9.5 times 10 to the minus 1. Now we can express all these in standard form, so let me just do that quickly. So this is 2.75. Alright, so this would be our values now expressed in standard form. Now what we see now is that we're just plotting values from 1 to about 10, or from 0 to about 10. Right. Similarly, we're plotting values from about from 0 to about 0.7. So we can look at the values as such, which will probably alleviate some of the challenges when it comes on to choosing a scale for these small values. And we could have also expressed these in standard form as well if we choose to do so. So let me just do that just for the sake of this. So this now becomes 1 times 10 to the minus 1, 2 times 10 to the minus 1, 4 times 10 to the minus 1, 6 times 10 to the minus 1, and 7 times 10 to the minus 1. No, as I said, this is just to allow us to be able to work with these values much easier. So now we have on the y-axis induced EMF, which goes from roughly 0 to about 10. So we're going to make a scale that can take us from 0 to about 10. So let's say we say every 2 centimeters we increase by 1. So this is 1.0. Let me just use 1. This would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now, our induced EMF, these values were actually raised to the power of 10 to the minus 1. So as such, we can include our multiplier. So we're going to say times 10 to the minus 1 to remind us that all these values are being multiplied by 10 to the minus 1. Now for the x-axis now, we have the induced EMF, which goes from 1 to about 7. So we can probably use the same scale on the x-axis. So we see now that, it's a pretty straightforward scale that we're working with. So this is 1, 2, 3, 4, 5, 6, 7, 8. And again, just like the y-axis, we have to include that this is 10 to the minus 1. So now, one thing that we also need to do is we need to indicate the scale that we use. So on the x-axis, we use 2 centimeters. Every 2 centimeters equal 1 times 10 to the minus 1. And since its speed is going to be meter per second. While for the y-axis now, we use a scale of, same scale, but 2 centimeters equals 1 times 10 to the minus 1 volt. So that's our scale. So we also want to include that, when we are plotting our graph. So next thing we can do now is we can now start to plot our points. So let's do that now. So we have 1.13 on the y and 1 on the x. So that's 1. This is 1, 1.1, 1.13. So we can estimate that to be about right there. All right. So 1.13. So we find 1.1 and we estimate where 0.03 would be. And that plots to 1 on the x. Next one quickly. 2.75 to 2. So 2 on the x, 2, 2.5, 2.6, 2.7. So 2.75 is going to be in the middle, thereabout. Next one going up, 5.38 to 4. So that's 4, 5.3, so 5, 5.1, 5.2, 5.3. 5.3 is going to be close to 5.4, so we could estimate it to be about there. So what we're trying to do is trying to reasonably estimate the location of the points. So 6.75 to 5. 6.75 to 5, so 5 right here. 6.75 to 6, 6.5, 6.6, 6.7, 6.75 again is going to be in the middle. Think about that. Next one, 7.5 to 6. 6, 7.5, so it's going to be right here. So that one goes there. And then our last point now is 9.5 to 7. So 7 on the x, 9.5. So 7, 9.5 is right there. So those are our points plotted. Now we're asked to, well, since we have our points like this, we're going to be required to draw a straight line through the points. So we're going to get to a ruler and line up like that. And we're going to aim to get an even distribution such that, you know, we have equal amounts of points on either side of the best fit line. So if we were to draw this line, we see that, I mean, we have 1, 2 on this side. If I maybe go like this, we have 1 on this side, and we have these two, and we could say that, okay, these two would compensate for that. So we draw our straight line like that. So that would be our best fit line. Now, next thing that we need to do is we need to ensure that we put in our title. So we're going to say graph showing All right, I'm going to say induced EMF. Let's write out induced EMF versus speed. Right, and then we just underline that. So that's our title. Right, pretty straightforward. Right, so that's that. Now, after we have done that, it says that we need to use the graph to determine the gradient G. So we can say that our gradient G, and it's always wise to use the symbol as they give in the question. So the gradient G is equal to y subscript 2 minus y subscript 1 divided by x subscript 2 minus x subscript 1. And we should be quite comfortable with, once we get a straight line graph, we're going to be required to find the gradient. So to do that, I'm going to be required to select 2 points that are far from each other, and then use that to work out my gradient. So I'm going to select 2 points, and the points that I'm selecting, I will be cautious to ensure that, you know, they are not corresponding to any of the plotted points, or in other words, any of the points that came from the table. So go like this, and then go across here, and notice I'm starting from the best fit line to either axis so that I don't miss the point on the best fit line, because we need to use points on the best fit line. But again, those should not be represented by any values in the table. So I'm using these 2 points, and notice that they are far apart. So in this case now, this would be my y2, and y2, this is 8.5, 8.6, 8.7, 8.8. So 8.8, and again, remember, times 10 to the minus 1, and this is volt. Similarly, I can read off y1, that's going to be 2 times 10 to the minus 1, and that's volt. While x2 now, that's going to be 6.5 times 10 to the minus 1, and this is meter per second. And x1 is 1.6 10 to the minus 1 meter per second. So with those values now, I can now find my gradient. So this was 8.8 times 10 to the minus 1 meter per second. Next one is 2. So minus 2 times 10 to the minus 1 meter per second. And x2 now is 6.5, and x1 is 1.6. So 6.5, 1.6. 6.5 times 10 to the minus 1 meter per second minus 1.6 times 10 to the minus 1 meter per second. Now, I notice that on the y-axis, I have volts and not meter per second. So let me just correct that. So these would be volt, volt. So now, simplifying this now, this is going to be 6.8 times 10 to the minus 1 volt divided by 6.5 minus that, that's going to be what now? 5.5. So 4.9 times 10 to the minus 1 meter per second. Now what we see now is that since we have 10 to the minus 1 and 10 to the minus 1 right here, they both cancel off. So we now have 6.8 divided by 4.9. So let's take in the calculator quickly. 6.8 minus 4.9. Sorry. 6.8 divided by 4.9. That's going to give me 1.39. So our gradient G then now is going to be 1.39. So that's 1.39. And after we calculate, we always want to write our unit. So it's volt per meter per second. Or we would say this is volt per meter per second. Well, per meter second. Or we could say volt second per meter. Or let me just write this as volt second per meter. So that will be our unit. Volt second per meter. So that would be the value for our gradient. Now sometimes when we do these kind of calculations, the unit themselves might not be making sense to us initially, but we always want to be guided by determining the unit for the gradient by considering the unit on the y-axis divided by the unit on the x-axis.